So let us continue our discussion on problems on VCRS. Now we'll be actually looking for a problem in VCRS which uses a heat exchanger. We know there are many subcooling methods available in VCRS, and subcooling is the only technique for improving the refrigerating effect and hence the COP of a VCRS system. And the subcooling can be done by numerous amount of methods, including the usage of a heat exchanger. So we'll be discussing regarding how to solve the problem when a heat exchanger with VCRS or a VCRS with heat exchanger comes, and how we can solve the problem related to that. So here we can see a heat exchanger as shown here is actually placed between the condenser, compressor, our capillary tube, evaporator, etc. As such, the of the uh, one side of the heat exchanger actually receives the high pressure liquid from the condenser, that is at state T3 dash as specified in our graph, or it is nothing but the saturated liquid which will be passing through this left side tube, while the other side actually receives the low pressure, high temperature vapor refrigerant, that is our saturated vapor, something at 1 dash. It will be received on the other side of the heat exchanger as shown here. So here we can see in our graph the points, that is 1 dash points, 1 dash, 2 dash, 3 dash, 4 dash, that is most probably the black lines, black thick lines actually represent a very simple or an ideal VCRS. That is 1 dash, 2 dash, 3 dash, 4 dash, which is nothing but our ideal VCRS. So into that VCRS, actually we are also adding an additional heat exchanger, which is mainly aids in subcooling the refrigerant. That is, as the point 3 dash or the refrigerant liquid which is coming out of the condenser will be more cooled much more. As such, the point 3 dash actually shift to a point outside the curve 3, where 3 dash and 3 actually lie in the same horizontal line. As such, instead of going to 4 dash, the refrigerant will be expanded to a point 4. As such, our refrigerating effect, that is the enthalpy difference, now has increased to 4 to 1 dash instead of 4 to 1. So the refrigerating effect is increasing. So the COP is also increasing, since COP is refrigerating effect by work done. Now, since we are using this heat exchanger, what is happening is that the vapor coming from the evaporator is, that is low pressure, high temperature vapor coming from the evaporator is going through one side, while low temperature, high pressure liquid refrigerant is coming through one side. As such, due to the pressure difference, the vapor is actually absorbing the temperature from the liquid refrigerant. That is why the temperature of the liquid refrigerant is actually decreasing from 3 dash to 3. We can see 3 dash enthalpy will be something like here, and the enthalpy of 3 will be something like here, and enthalpy is nothing but the heat contained in a fluid or system we consider. So as the enthalpy is reducing, the temperature is also decreasing drastically. But at the same time, the heat taken by the evaporator is also getting heated up. That is, the evaporator actually, this is 1 dash radar, evaporator, uh, the evaporator actually entering the compressor, or before entering the compressor was at our saturated vapor, and it actually takes heat and it gets converted to a superheated vapor even before entry into the compressor. So it is also taking up the heat, and with the use of this heat exchanger, even though some work is being done for heating or some extra work is needed for compressing the superheated vapor, we can keep in mind that no liquid actually gets inside this compressor. So this is actually an advantage for our VCRS, which actually gives a more subcooling or refrigerating effect, as well as avoids any damage to the compressor due to the entry of liquid particles. So the refrigerant or saturated vapor will be made devoid of any liquid particles. That is, it is getting converted from 1 dash to 1, or it is getting heated from 1 dash to 1, and this difference, that is the temperature difference between 1 and 1 dash, is actually specified as our degree of superheating, since the point is actually shifting to the right side of the curve. Also, this 1 dash and 1 also lies in the same horizontal line as the evaporator. That is, the pressure for the both points are same only evaporator pressure. Similarly, here 3 and 3 dash lies in the same point. That is, the pressure for the points 3 dash, that is the liquid refrigerant coming out of the condenser, as well as the subcooled liquid will be same only. That is the condenser pressure or temperature only. And the difference between the temperature, that is T3 dash minus T3, is actually called as degree of subcooling or supercooling. This will be 1. Okay, so that is the effect of a VCRS with a heat exchanger. Now, if the heat exchanger used is given by the term something like liquid suction heat exchanger, or is given by the term something like liquid suction heat exchanger, or it is given as LSHX. In our question, the degree of superheating the vapor refrigerant will be same as the degree of supercooling the refrigerant. That is, degree of superheating, that is the 1 dash to 1 will be same as 3 dash to 3, or T1 dash, the temperature difference, that is T1 dash, T1 minus T1 dash will be same as T3 dash minus T3 if a special heat exchanger like liquid suction heat exchanger is being used for our VCRS. Okay. Now coming to our question, it is given as a freezer of 20 ton capacity, tons of refrigeration capacity, has an evaporator and condenser temperature of minus 30 and 25 degrees Celsius respectively. The refrigerant R12 is subcooled by 5 degrees Celsius before entering the expansion valve, and it is also superheated by 5 degrees Celsius before entering the evaporator. So the degree of subcooling and superheating is given by equal amount of 5 degrees Celsius. That is, the refrigerant coming out of the condenser is again cooled by 5 degrees Celsius below, while the vapor refrigerant coming out of the evaporator is again heated to by 5 degrees Celsius to superheated state before entering the compressor. This is not evaporator, this is compressor. If a six-cylinder single acting compressor with stroke equal to bore running at 1000 rpm is used, determine the COP, theoretical piston displacement per minute, theoretical bore and stroke. So that is our question. We have written our actual PS diagram with a heat exchanger. So 1, 2, 3, 4 being the area we have to take, while 1 dash, 2 dash, 3 dash, 4 dash actually belongs to the ideal VCRS. Also, this temperature difference between 1 dash and 1 is 5 degrees Celsius. Also, the temperature difference between 3 and 3 dash is 5 degrees Celsius. And this is lying at the above horizontal line lying at condenser temperature of 25 degrees Celsius, and the below line is lying at evaporator temperature of minus 30 degrees Celsius, and the refrigerant we are going to use here is R12, and the data given is mainly given by the evaporator temperature as minus 30 or 243 Kelvin, the condenser temperature as 25 or 298 Kelvin, the degree of subcooling as 5 degrees Celsius. That is nothing but T3 dash minus T3 that is T3 dash minus T3. Also, the degree of superheating is given as 5 degrees Celsius. That is T1 minus T1 dash. Now, since both are equal, we can assume here we are using a liquid to suction heat exchanger here. Also, the number of cylinders of the compressor as 6, and the compressor is a single acting compressor with L is equal to D, that is stroke is equal to bore, that is L and bore diameter of the cylinder are same. Also, the speed of the compressor is specified as 1000 rpm. So these are the data given in the question. Now we'll be taking the values of R12 corresponding to minus 30 and 25 degrees Celsius, namely the specific volume Vg HF, HG, SF and SG. Also, the refrigerating effect is actually given in terms of 20 tons of refrigeration, which we need to convert into our kilowatts for doing our analysis, which is nothing but 70 kilowatt. And since there is no value regarding the specific heat of vapor or specific heat of liquid refrigerant is given, since this value is not given, it is better to do this problem graphically. So we have actually taken the chart for R12 as shown here, and we know the refrigerant temperature, the evaporator temperature as minus 30 degrees Celsius and the condenser temperature as plus 25 degrees Celsius, the point being here and here respectively. So first of all, we'll be actually drawing a horizontal line through minus 30 degrees Celsius inside the dome, and next we'll be drawing a horizontal line through 25 degrees Celsius, that is condenser temperature inside the dome, and we are going to extend that rightwards horizontally for finding our second point, state 2 or after compression point. Now we know that the refrigerant has been superheated by 5 degrees Celsius as well as subcooled by 5 degrees Celsius. So here, instead of 1, the 1 will be actually shifted horizontally by 5 degrees Celsius towards right. Similarly, the refrigerant coming from the condenser will be subcooled, that will be shifted by 5 degrees Celsius towards the left side. Also, the graphs or scale shown here actually gives the temperature difference or superheating effect in terms of minus 50, 50, etc., where 5 units is equivalent to 50 degrees Celsius. So using that concept here, single unit or the single distance is actually equivalent to 10 degrees Celsius. So we need a 5 degrees Celsius difference. So taking the half of the value, we will actually using that length, we will be extending the our evaporator temperature line towards right horizontally by taking this value almost equal to 5 degrees Celsius. That is here 1 unit, that is up to here is equivalent to 10 degrees Celsius. So half of that length is equivalent to 5 degrees Celsius. That length is actually extended towards right in our evaporator line towards superheated state, since superheated before entry to the compressor. Also, the same length is actually extended after coming out of the condenser from saturated liquid towards left. That is, both the red lines here are of same length and they represents a 5 degrees Celsius temperature difference, which is nothing but the length taken from this scale here rather, and this much length is actually equivalent to 10 degrees Celsius. Then we got our point before compression. Then also these red lines actually represents our constant entropy lines. So from our compressor entry, we'll draw a constant entropy line or a line parallel to this. As such, this will be cutting through our condenser temperature line. This was actually 25 degrees Celsius, and this was actually minus 30 degrees Celsius, and this much temperature difference was plus 5, and this much temperature difference was minus 5 since cooling here. Similarly, from point 3, we'll be drawing a perpendicular for actually showing it is an isenthalpic expansion rather. So we'll get our points something like this as 1, 2, 3 and 4. In our next step, we'll be taking the enthalpies from these points by dropping a perpendicular towards the x-axis for finding the enthalpies from all the points 1, 2, 3 and 4. So first of all, dropping from 1, so we can get the value of enthalpy at 1 to be nearly equivalent to 190 kilojoules per kilogram. Similarly, enthalpy at 2, which will be nearly 225 to 230 kilojoules per kilogram, and enthalpy at 3 and 4 will be nearly 50 to 55 kilojoules per kilogram. So by taking the values with atmosphere, we'll get the values of enthalpy at 1 as 187, enthalpy at 2, state 2 as 225, enthalpy at 3 at 54 as well as 4 at 54. Now we need to find the COP. COP is actually given by refrigerating effect by work done. Already we know the refrigerating effect, that is, we know the enthalpies, that is H1 minus H4 by H2 minus H1. By substituting the values as tabled below, we'll get the COP to be around 3.5. Now, the next thing will be is to find the theoretical piston displacement, that is nothing but the capital V dot corresponding to the entry to the compressor. For that, we can use the formula mass flow rate of the refrigerant into specific volume at 1 divided by compressor efficiency, or we can also use our LANK by 60 formula. Both are applicable here. So for that, for finding the theoretical piston displacement, first of all, we need to find the mass flow rate of the refrigerant. We already know the refrigerating effect, which is equal to 20 tons of refrigeration or 70 kilowatt. Also, this 20 tons of refrigeration is also equivalent to m dot mass flow rate of the refrigerant in kilogram per second into enthalpy difference in kilojoules per kilogram. That is enthalpy difference or the enthalpy of evaporation, enthalpy difference during evaporation. So using that formula, we'll get 70 kilowatts to be equal to m dot in kilowatts into 187 minus 84, which gives our mass flow rate of the refrigerant to be equivalent to 0.526 kilograms per second. Similarly, we need to find the specific volume, that is small v1 of the refrigerant vapor or superheated vapor before entering the compressor. That can be easily found out from the graph, but the trouble with the graph is that it is a bit difficult to find the exact values, since this enthalpy lines are almost going something like this between the log of -1 and 0. So better we can use the analytical formula here. That would be a much better option. That is, for that, first of all, we need to take, we know that near this one is our 1 dash point, that is before superheating. So volume at 1 is nothing but Vg value at minus 30 degrees Celsius, which is nothing but 0.1596 meter cube per kilogram. Also, we know that for this point, pressure is equal to constant. Okay, pressure is equal to constant. We also know here the ideal gas relation actually stays here. That is the relation between 1 dash and 1, that is P1 V1 by T1 can be written as P1 dash V1 dash, that is we'll take here volume as specific volume V1 dash by T1 dash. We know here at P1 and P1 dash both the pressures are same, so we can write V1 by T1 can be written as V1 dash by T1 dash. Also here T1 dash is nothing but our evaporator temperature but in Kelvin rather, and T1 is nothing but the evaporator temperature plus 5 degrees Celsius, which is converted to Kelvin. So by using our ideal gas equation, which is reduced using the concept of Charles law, we have V1 by V1 dash is equal to T1 by T1 dash, or we have V1 by V1 dash is 0.1596 is equal to T1 is nothing but our evaporator temperature plus a superheated value, that is minus 30 plus 5, which is converted to Kelvin plus 273. Mind you, the temperature should be in Kelvin, as in ideal gas law, the temperature should be taken in Kelvin, divided by T1 dash is nothing but our evaporator temperature, which is nothing but minus 30 plus 273. Upon solving this value, we'll get 248 by 243 is equal to V1 by 0.1596, or V1 is equal to 0.1629 meter cube per kilogram. Even though the method is slightly longer compared to the graphical method, we can actually get an accurate result when we use this Charles law or V1 by T1 form. Okay. Now, you need to find the piston displacement, which is given by mass flow rate of the refrigerant into specific volume at 1, which we now found out by compressor efficiency. Since this is not given, we'll assume that to be 1 rather. It becomes 0.263 into 0.1629 we'll get the value to be 0.08573 meter cube per second, or that will come to be around, by 60 it comes to be around 5.14 meter cube per minute. Now we also need to find the theoretical bore and stroke of the piston, that is d comma l values. We already know it is given in the question, bore is equal to stroke, or diameter of the cylinder is equal to the length of stroke of the cylinder, d is equal to l. Also we have the number of cylinders as k is equal to 6, and it is given it is a single acting cylinder. Also it is given speed n is equal to 1000 rpm. If it was double acting, we had to substitute 2000, that is into 2 instead of 1000. Since it is single acting, we can directly substitute speed as 1000 rpm. Then piston displacement in meter cube per second, which already we find out previously, can also be written as LANK by 60, that is stroke into area of the bore into speed into number of cylinders by 60, or 0.04284. 0.04284 is actually equivalent to L into pi into d square into 1000 into 6 by 4 into 60, which is equal to, which will get, by substituting for d is equal to L, we'll get a cubical equation in terms of L or d, and since d is equal to L, by solving for this cube root, we'll get the diameter or the length of the cylinder as 0.103 meters, or it will be 103 mm. Here actually the piston displacement is actually 0.857, but if you could check the answer will be 103 mm or 0.103 meters only. Thank you.